Hello friends and welcome back. In this video we will be talking about rotational motion, kind of a straightforward application but very interesting application of circular motion that we've already studied before, and the related topic of moment of inertia, which is a very important quantity in physics that generalizes the role of mass essentially for rotating objects. So let's jump right into it. You may remember from week 1, circular motion, that if we have an object that is moving on a circular trajectory around a point, a central point at a distance r, then there's several things that we define, namely, well, we called the angle phi that indicates the position, the angular position on the circumference of this object. We wrote all the equations for the coordinates x and y, for example. We said that velocity is tangential and it's equal to omega r, where this omega is the angular velocity, and namely the rate of change of the angle phi, angular velocity. And we said, for example, that the acceleration of this object has two components: a centripetal component that is always pointing towards the center of the circle, and a tangential component, potentially, that doesn't have to be there, but it may be there. That is related to the fact to whether the object is speeding up or slowing down. So this is v squared over r, which is the same as omega squared r. And the tangential component, if it's there, it's equal to alpha r, where alpha is the angular acceleration. So this alpha is the second derivative of phi with respect to t, or the derivative of omega with respect to t, times the radius. Okay, wonderful. Now, if we take all this and we extend it, or we utilize the same language but to describe a physical object, let's say a little blob like this, that collectively is rotating around a certain pivot. So all of this thing is turning around. So each point will have a certain distance from the center, a certain physical velocity, but all at the same angular velocity. Okay, so we'd like to be able to describe this motion, which happens all the time. If you, I don't know, spin a yo-yo, or the wheels of your bike as you're riding it to PHS or wherever. There's a lot of applications of rotational motions, the motion of objects that rotate. Okay, and in particular, it's an interesting question to ask: what is the energy that is associated with this motion? It's probably easy to have the intuition that it's somehow a type of kinetic energy, because every little bit, let's say that there's a little element dm of this object, and this has it brings a kinetic energy which is 1/2 dm times v squared, or equivalently 1/2 dm times omega r squared. So if I add all of these little contributions, then it turns out that the total kinetic energy of this blob that is collectively rotating is the sum of all of these contributions. So it's the little mi, where mi is the mass of the element of my system labeled I, times omega squared times Ri squared. Notice that both m and r depend on the specific element that I'm considering, whereas omega, the angular velocity, as I mentioned just now, that's the same for everybody. Okay. So all in all, I can write this thing as 1/2 this weird summation of the masses times the distance from the center squared, and then multiplying everything omega squared. It looks complicated and odd, but it's already a little bit attractive, because as we said, this omega is a universal thing that just depends on how quick this object is rotating, how quickly. And this thing, as you can see, does not depend on the type of rotation, on the speed of rotation or anything. It's sort of a property of the object. You just need to count all the mass elements that this object is made of and their distances from the axis of rotation. And this object here, let me zoom out a second. There we go. Let me put it here. This object that I'm going to rewrite just now, so the sum of the masses that my system is made of and their distance squared from the center, the rotation axis, is called capital I, and it's the famous moment of inertia, or rotational inertia. All right, very important. All right. There's an asterisk here or everywhere, and this asterisk is that it's not, the moment of inertia is not only a property of the object I'm considering, but it's also a property of the, or it depends on the rotation axis that I chose. So completely depends on the chosen rotation axis. Namely, the same object will have a different moment of inertia if I choose a different axis of rotation, if I spin it around a different point. You can probably figure this out. Let's say, let me color this in to show that this is a physical blob. This will have a different type of rotation if I spin it around a point here, or if I, let's say, spin it around this point. Okay, you can probably imagine in the first case, let's call it 1, this whole thing is more or less, looks like it's kind of centered around its center of mass, more or less. And so it's going to spin quite easily, or relatively easily. Whereas if I try to spin it around 2, the whole thing needs to rotate around it. It's gonna, it seems intuitive that it should be more difficult, or at least a different type of rotational inertia. Okay, so again, and you can see it explicitly because these distances change, obviously, depending on the chosen axis, right? So all in all, and I had deleted a couple letters accidentally. So the punchline of this slide, let's call it that, is the definition of moment of inertia, which we just gave, and the fact that the kinetic energy associated with the rotation of this object is 1/2 I, so moment of inertia, omega squared. Okay. Now, if there's both a rotation of the object and a translation, so you have to imagine that this blob that I'm considering, not only is it rotating around, maybe let's change color, rotating around a certain axis, but it's also collectively moving with a certain certain velocity, then the total kinetic energy, associated with this motion is the sum of the rotational component that we just talked about, plus the usual translational part, translational kinetic energy. And so this is equal to 1/2 the moment of inertia around center of mass, omega squared, plus the usual 1/2 total mass and the speed of the center of mass squared. Okay, so there are instances in which, and we will study one very famous application, which is rolling motion of this situation, where you have both an object that is moving collectively in space and also spinning or rotating, and in that case you have this type of expression. I should give you a little caveat that this is always about the center of mass, even though in principle an object may be rotating around a different axis and not an axis that passes through the center of mass, in which case this expression is still valid, but the rotational term might be a little more complicated to write down. But let's not get into these unnecessary details. So every single time we study something like that, a mixed motion in this course, it will be with rotations around the center of mass, so we're safe. And this is the expression you want to use. All right. Wonderful. Thank you so much for watching, and I'll see you soon.